In this video, I'm going to go through required practical 7, which involves the simple motion of a simple pendulum and a mass spring system like the one shown in the diagram. In my class, you'll be tested on the following CPACs. 2B, that you can time small oscillations and check they're all in one plane, that you take multiple readings and you're doing them correctly, and that you can set up the equipment yourself. I'm going to go through the method for the simple pendulum first. Get a marker and place it in the center. So for digital marker, for example, I used a pin attached to some blue tack, and I placed it in the center because that's where the uncertainty in the position of the ball as it swings is at its lowest in the center. Okay, then you need to measure the length of the pendulum. The length is from the point where it's attached to the center of mass. So if you have a ball like I have here, you may want to measure the diameter of the ball, divide that by 2 to get the radius, and then add that to the length of the string that you're using. Simple harmonic motion is only when you use less than 10 degrees of displacement, because otherwise it can't use a simple small angle approximation. So make sure you don't displace it beyond 10 degrees when you displace and release it. And then it's going to oscillate back and forth, but sometimes it goes in circles, and you want to avoid that. Make sure that it only oscillates in one plane. You're going to time 10 oscillations, because if you time one oscillation, the percentage uncertainty in that will be too large. So time at least 10 oscillations, and then you can divide that by 10 to get your time period. Then repeat this process again, but with a different length. So do that at least 6-7 times for different lengths. Then you've got your data and record that into your table. And now for the mass spring system. Get a fiducial marker and attach it to the equilibrium position like shown in the diagram here. I'm measuring it to the bottom of the mass. Okay, and then actually the masses are independent variables, so you have to measure that first. So use an electronic balance to measure the mass that you're using, and then you're going to pull it down and just a bit, not too much, so that it doesn't oscillate violently. So just do a bit and then let it oscillate up and down. Make sure it's oscillating vertically. Sometimes it tends to go left and right, and you want to avoid doing that. And then time at least 10 oscillations to reduce the percentage uncertainty. And then you can repeat this whole process again with a different mass, slightly heavier, but making sure you don't go beyond the limit of proportionality or the elastic limit. And again, keeping the oscillations fairly small. Before you start the practical, make sure you have a table to record your results. Here's the one for the simple pendulum. So I'm changing the length, at least 6 sets of readings, and I'm timing 10 oscillations, but at least 3 times. And I'm going to find the average of that and then divide that by 10 because I'm doing 10 oscillations and I only want the time period, which is for one oscillation. So, and then write that down in the column. Another useful column to have is time period squared in seconds squared, because you're going to use this to plot a graph later. Here's the one for the mass spring system. Here I'm changing the mass. Again, I'm doing 5 sets of data here, but if you're able to do more, that's fine, but just don't go beyond the limit of proportionality and don't put too much weight on the spring because it could topple over and it could become a bit dangerous if it snaps. Again, you might want to add another column for time period squared, which you'll use to plot a graph later on. Once you've carried out the practical, you need to complete the following discussions in the discussion section of your lab booklet. So how did you reduce the percentage uncertainty in the measurement of the time period? So did you measure just one oscillation, which would have a very large percentage uncertainty, or did you measure multiple oscillations? You then give some details into how you measured the oscillations and when did you start the time and how did you avoid miscounting the number of oscillations. So my advice would be to use your mobile phones to record the oscillations with the stopwatch running in the background. So this way you can use the slow motion feature of your cameras to slow it down the video clip afterwards and start your timer and really count carefully each oscillation and obviously measure the time period of over 10 oscillations at least, and that way you're less likely to miscount it. And then you can also get your partner that you're working with to do it themselves independently, and then you confirm that you haven't overcounted by one oscillation, or sometimes people count half oscillation instead of measuring one whole oscillation. So make sure you avoid that mistake. And then you can discuss why use small amplitude oscillations. So for example, about the small angle approximation and why that's important. You can also discuss any other issue you encountered and how you overcame it during the practical. So for example, was your pendulum oscillating in one plane, or was it going back and forth or round in circles, and how you avoided it from doing that. These final steps aren't essential to pass the CPACs in my class, but I do recommend them. So we've got the time period as a function of the length of the pendulum and the gravitational field strength. and we're gonna plot a graph. Okay, so if you plot time period against length, it won't be a straight line. So what I recommend is squaring both sides, so it becomes time period squared 4 pi squared L over G. So the square root is gone now. And then compare it to the equation of line y equals mx plus c. On the y-axis you can plot time squared. On the x-axis you can plot the length, which is what we changed. And if you can look at it, so you should get a straight line and you should be going through the origin. There shouldn't be a y-intercept. And if you look at what's multiplying the length, which is the thing that's in front of the x, which is the gradient, you should get 4 pi squared over g as your gradient. So therefore, the gravitational field strength, which should be 9.81 on the surface of Earth, is going to be 4 pi squared over the gradient. You can do this for the mass spring system as well. So we've got time period as a function of mass and spring constant. So square both sides. So we've got time period squared, 4 pi squared m over k. So it's don't have the square root anymore. Compared to y equals mx plus c. On the y-axis, plot time period squared, and the units is seconds squared there. And then on the x-axis, you can plot m, which is what we changed the mass in kilograms. You should get a straight line going through the origin. There shouldn't be a y-intercept. And the gradient should be 4 pi squared divided by k. Okay, so that's our gradient there. So therefore, the spring constant will equal 4 pi squared divided by the gradient.